Hello? Hello? Okay. Good afternoon, everyone. Let's start. Sorry, the small little microphone. The battery is dead again, so I have to adapt to this more powerful one. I'll try to make sure to be far away from this microphone. Okay. Okay. So first of all, we released the homework 4 today. So if you have some chance, please take a look. They're just asking you to calculate the expectation and several expectations according to what we had discussed in the previous lectures. So the workload is quite light. So if you have some chance, please start working early. And we don't have we won't want to take your time on spring break. So the deadline will be 1 week after the spring break. So you should have like plenty of time doing this, but just be aware there is a homework assignment. And also our quiz this week will be available after today's class, and feel free to take it before Friday midnight. And again, 20 minutes to choice problems. You should have sufficient time, but don't just open it and let the time go. Okay. Okay, so let us wrap up with the variance. So in the last lecture, we introduced the concept of variance. So we say that, okay, for any random variable, actually, we're looking into its probability mass function if this is a discrete random variable, and then probability density function, PDF, if it's continuous random variable, right? But because random variable, we know the random variable can have multiple values. If you observe, like if you do some observation over the random experiments or random phenomenon like stock price, like ETF, like precipitation, snow amount, range of, all those are random, right? If you model them as random variables, you say different experiments will have different outcomes. Their values are uncertain, so can take multiple values. So that's why like people are interested to know what is the average behavior of those random variables. That's why I want to look at, okay, what's the expectation and what is the variance, right? So what's the expectation? Can anyone give a hint? What's the expectation of random variable? Yeah, the average, right? But here, just be careful. This is a weighted average. This is just not the simple average, because the random variable can take different values with different chance, right? It's not like it is gonna take every possible value with equal chance. If that's the case, this random variable is called a uniform random variable, right? And in many cases, like random variables might have like much higher chance to take one set of values than taking another set of values, right? So the expectation will be you are doing a weighted average of all possible values the random variable can take. And the weight is the probability density function value at that value, right? Okay. So if you write it down like expectation is, in general, we're doing integration, right? We're doing integration. We're going to integrate x. Usually the range is minus infinity to infinity, and times the probability density function. You just integrate this guy. Okay. So you got the average, right? This fx is the PDF function. Right? That's why we call the weighted average. Of course, when x is a discrete random variable, integration will be reduced to a summation, and the PDF will reduce to the PMF, right? So it becomes a summation of every value X can take, weighted by the probability X takes this value, right? So that's the definition of expectation. So expectation, I mean, it is entirely motivated by this sense of average. Then it comes to variance. So what does variance represent? What's the intuitive yes, exactly, right? So you want to supplement anything? Okay, so do you want to supplement anything? Okay, great. So if you look at the random variable, right, suppose this is just these values are just distributed across this x-axis, right? So it has possible value to take here, 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 here. It has less likely chance to be far away, right? So it's very likely to be here, right? So if we take the weighted average of all the possible values X can take according to their PDF, you know the average value will be surrounding here, right? So average X will take value here. But this is just talking about on average how this value can take, right? There's another important thing we want to look at is on average how far away your X will get away from the average or the expectation. So this is characterized by the so-called variance. So basically, you can imagine every time you observe the value of random variable, this time it could be here, this time it could be here, this time it could be here, right? So every time the distance or the difference from the average will be like this, right? You just record every time when you re-observe these random variables, you look at their deviation from the average or from the expectation, you take the average of those deviations. That's where you're gonna see the variance. Okay. So formally, the variance is defined as another expectation. You're gonna look at the square difference between X and its expectation, okay? And then you take expectation. Why is that? So if you take a look at here, right? X minus EX squared is actually a function of X. Right? It is determined by X, right? So it's a function of X. So you're gonna take an expectation of a function of X. How do you calculate an expectation of a function of a random variable? With, yeah, of course, we're gonna integrate the PDF. With whom? Yeah, the phase function of g of x, right? So if you want to calculate expectation of a function of x, right, you just replace x by the function of x in the expectation formula. That's it. Right? That's how we compute the variance. Everyone is comfortable? Okay, so I mean to further, because the variance is computed actually based on the square of the difference, right? So that actually the unit is not the same as the original value of your expectation. So if you want to be more comfortable, standard deviation is something we should consider. Standard deviation is just taking the square root of the variance. So once you take the square root, you can imagine, okay, this deviation will be on the same scale as the expectation and also on the value X can take, which can make your analysis a little bit more comfortable and more convenient. That's the motivation of the standard deviation. And we briefly mentioned that in the future, you will see that people always use standard deviation to construct some like confidence intervals to do some hypothesis testing. So basically, if you want to probe what's the property of a unknown random variable. Right? In many cases, you don't know what's the random variable, what the distribution will the random variable respect, right? And so people were gonna make some hypothesis, meaning that they guess, okay, this X follows some distribution, say Gaussian distribution. Then if X really follows some Gaussian distribution, they can construct some confidence interval, which is centered at the expectation and extended both right and to the right and left with a standard deviation. And then X should has a very large chance to fall in this range, this interval, right? You can calculate that based on the PDF. And if your hypothesis is incorrect, what does it mean? It means that when we look at the value of X, the actual value of X, meaning just look at one value of X. If X falls far away from this interval, that is abnormal because that will mean that your observation of X is a rare event. It's like, okay, if you believe for example, if you're abducted, for example, and you're not allowed to see anything, and people throw you into some place, you don't know where you are, right? And you want to know, okay, where am I, right? Where I am. I make a hypothesis. Maybe I'm in the North Pole. I'm in the North Pole. And so what should I do, right? How should I verify I'm in the North Pole? I can't see anything, right? But I might have some like a temperature gauge, right? Which can tells me, like maybe I just call Siri, tell me what's the temperature outside. And temperature, and the Siri responded, okay, it is like 100 degree of Fahrenheit, right? So you know your hypothesis will be wrong. It's not possible, right? Because you're assuming you're in the North Pole. That means like, okay, the temperature, if it is random variable, its distribution will be very concentrated on low degrees of Fahrenheit, right? Very low degrees of Fahrenheit. I may make you, if you heal it, it will freeze, something like that, right? But if you observe this random variable's value, the temperature's value, you find it's very, very high, right? Is according to the distribution, we assume that temperature should respect your observed temperature value is a rare event. Right? There's a basic principle in practice is called a rare event cannot appear in just one experiment. So if you just pick up just one rate, give you, okay, that's a high and unbelievable rate, then that can only means that your hypothesis is wrong. Right? That's the whole idea of the hypothesis testing. Right? And probably it turns out that, okay, you're just thrown out into, say, Bryce Canyon. It's not possible. Okay, I mean, this is just to give you like a brief sense about hypothesis testing, which is very widely used in science, engineering, the social science, all kinds of stuff. Okay. So we gave some like examples about how to compute the variance, like Bernoulli variables variance, variance of the Gaussian distribution, which we're gonna not repeat. And also, there is an equivalent formula to compute the variance. That is, we can also calculate the variance as the expectation of x squared subtracted by the square of the expectation, right? So you see the difference is in where you have this power 2 inside or outside the expectation. This location difference will give you different values, and their difference will be the variance value, right? We're not gonna prove this again, right? We hope that every one of you have replicated this proof, because it's like very classical trick. Many proof of lemmas in statistical literature leverage the same trick. Okay. So another important property about the variance is called the scaling property. So we know that the expectation has the linearity, right? It's very important property. I hope that everyone will keep it in mind, right? So what does the linearity means? If you take an expectation of a linear combination of random variables and constant, ax plus b, right? X here is a random variable, and a and b are both constants. So the expectation is the same as you first take the expectation of all the random variables, and then do the linear combination. So that means like you can put the expectation cross, you can move the expectation cross all the constant and just apply the expectation over the random variables, and the result exactly the same, right? So this one has many important applications that can greatly simplify many computation, right? For example, how do you compute the expectation of binomial random variables? And when we look at the variance, if we still do a linear combination of a random variable and a constant, say ax plus b, and it turns out that if you take in the variance, the constants will just disappear. Like if you add a constant, the constant will just disappear. And the constant coefficient will be squared. That is called the variance scaling property. So it's different from expectation, right? So the variance of a times x plus b is equal to a squared times variance of x. Okay? So this is also a very important property. I hope everyone will keep it in mind. So the proof is really straightforward. You just follow the definition of the expectation and doing some kind of simple primary school math practice. You'll get that, right? The interesting thing is that, okay, for the expectation, you're going to keep the constant. You're going to multiply the original constant, but in the variance case, you're going to remove the constant you add, and you take the constant coefficient square. Okay, any questions so far? Okay. So one last example we want to show the variance, right, is about this rolling dice example. So suppose we roll a 6-sided die, meaning and you got an equal chance to say any point. So basically means that your probability to say every point is 1/6. So this point ranges from 1, 2 until 6. Okay. So now, if I want to calculate the variance, we can use a formula, right? So the variance, here we're going to use the second formula about the variance. now the original formula, which is expectation of x squared subtracted square of expectation. Right. So how do we compute expectation of x squared? Any thought? Remember, how do we compute the expectation of function of x? X squared is just a function of x, right? Yeah, you just integrate your, here is a discrete and variable, you just do a summation, right? And now you're gonna do a weighted summation of the function value, every possible function value, right? And the function here is just square function. That's why we do this, right? The weight is the same, 1/6, right? And then you evaluate the function value at every possible value x takes, which is x squared. So you have this summation of the side, you can say, right? 1 through 6, and you have weight, which is the probability you say the side, the point is k, right? Times k squared, right? That will give you the expectation of x squared. And then you subtract it by the square of expectation, right? This one we have calculated before. This is just simply the average, just simply the average of all values we have, right? Which is just 7/2, right? Now you just calculate difference between these two values. You got this number is approximately 2.92. And if you look at standard deviation, you just take the square root of that, which gives you like 1.71. Okay, any question regarding this example? Okay, so that's great. Okay, so next, we're going to talk about how do we characterize the relationship between multiple random variables. Okay. So that leads us to this so-called joint probability and independence for discrete random variables. Of course, there will be joint probability for continuous random variables, but we'll start with discrete random variables. So so far we will talk about PDF, PMF, expectation, variance, all kind of stuff. It's just for one random variable, right? Given a random variable, you want to look at on average what value it takes, and on average how it deviates from its expectation, and so on, right? But sometimes we're interested in looking at not only one random variable. Well, we're interested in jointly looking at multiple random variables. There are many such scenarios. For example, if you do the experiments multiple times, right? No matter your experiments are independent to each other or are related to each other, right? For example, if you just keep flipping a coin, you want to look at the sequence of heads and tails you have seen from many such kind of experiments. No matter, like if in many cases you're going to assume, okay, the flipping the coin are independent to each other, but I want to look at, okay, what's the joint chance that you see a sequence, a particular sequence like heads, tail. Not to mention, there are other cases like you have a series of experiments, but those experiments are not independent to each other. They're actually closely related to each other. Right? For example, there are some like uh, uh, like stocking, uh, the strategy is to buy and sell stocks, right? And your next step, your decision made by your next step actually is directly related to the outcome of the first step's decision, right? So actually those sequence of decisions are related to each other, not just doing that independently. For example, if you keep buying, if you if you look at the stock price is going higher, right? It's keep going high. Probably most people's strategy will keep buying, right? And if you look at the stock price going down, most people strategy will just selling, right? There will be very rare people like, okay, they're gonna buy when the stock prices goes down, right? And some are comes Warren Buffett, some comes got broken. So yeah, so in those cases, like people are not just looking into one experiment, one decision, or one outcome. They want to look at multiple outcomes. Or if you're doing some like a scientific experiment, in most cases, you're not just restricted to collecting one variable, right? You want to collect as many variables as you can. For example, if you're a climate scientist, right? If you build up some like observational sites, right? There are many of them, like in Utah, in mountains, in valleys, right? You see that, okay, they spend the uh, uh, hundreds of thousands of dollars or even $1 million to build an expensive device. They're not just looking to the temperature, right? They're trying to be designed to collect as many variables as possible. Right? For example, you might want to say, okay, temperature, barometric pressure, wind speed, precipitation, snow weight, and even like the strength of the sunlight and so on, right? So those random variables, yeah, I want to ask, what do you say about those random variables? Are they irrelevant to each other? They're not, right? So the wind speed and temperature are not usually not independent of each other, right? And considering the winter, right? If you are having like very high speed, the temperature usually is not very high. It's not usually is not be very warm, or if you see a lot of snow, right? Snow precipitation amount is large, right? Usually means like temperature is low. So it means that, okay, those random variables, although they represent different random phenomenon in nature, but there are some like very strong underlying connections. A third example is that, okay, we're not only trying to collect those random variables, we're trying to study the relationship between those variables, right? For example, how does human beings living habit associate with their health outcomes, right? How does lung cancer, will the smoking really lead to lung cancer? Right? Sleeping well will lead to happiness or depression, all kinds of stuff, right? Those are all like kind of like talking about the relationship between multiple random variables, not just one random variable. Or repeated measurements with errors, right? This is actually is also like often used in experiments, because if you do some real experiments, you find that you will never you always involve some errors, right? There's no way you're gonna get 100% accurate read, no way, right? So to reduce the error, there's a lot of theory talking about, okay, we should repeated measurements, and hopefully, for example, with the simplest strategy, I just average all the measurements together so that the errors can be averaged out under some kind of assumptions. So and doing this kind of like error reduction and error estimate also require us to learn what's the joint distribution of those random variables. Okay, so those are just a non-exhaustive list of motivations why we introduce joint probability density function. So what is a joint density function? Right? So we start with two random variables, and it is very easy to extend to multiple 3, 10, or even arbitrary large number of the random variables. Right? So let us consider x and y, the two discrete random variables. Again, we start with discrete random variables. So in our previous discussion, we know the random variable is a mapping from the sample space to some real number, right, to real space. Therefore, we kind of define a type of event like x equals to a. X equals to a represents the set of the outcomes such that the value of random variable is a. Right? This just represent a small subset. Maybe it's not small, but just a subset of samples or outcomes in the sample space whose corresponding random variable value is a. Okay? So we can define this is a particular type of event, right? X equals to a. And then here's our definition, right? So when we have two events, A and B, and A and B are two sets, remember, that's from the very beginning how we define the random event, right? Random events are represented as sets, right? So we define the joint probability of two events as the probability of the event A intersection with B. So if this is A, right, if this is B, the joint probability of A and B is defined as the probability of A intersection with B. Right? That is probability for this overlapping part. And in English, it means like, I want to know the probability that A and B both happen. Any questions so far? Everyone's comfortable? Okay, so now, how do we extrapolate this joint probability definition to the random variable case? So remember, according to the random variable, we can define the events like x equals to a and y equals to b. Right? Now, we can also talk about a new event, x equals to a and y equals to b. Right? So mathematically, it is said as like x equals to a intersection with y equals to b. In English, it means like x equals to a and y is equal to b. You can imagine this is a event which represents both the event x equals to a happens and the event y equals to b happens. Right? And then we use the probability of this event as the joint probability mass function for the two random variables x and y. The joint probability mass function for two random variables is two-dimensional function, meaning that has two inputs, A and B. So the joint probability mass function at A and B is defined as the joint probability of event x equals to A and y equals to B. Does it make sense? Any questions so far? And for concise, right? For being concise, like in people won't usually like always write the event as big bracket and something and as a set, right? So that's why in a textbook, what you can always say is that the joint probability is written as p of x equals to a, comma y equals to b. This actually represents the joint probability of the first event A, which is x equals to a, the first event B, which is y equals b. And the joint PMF is actually the joint probability of these two events. Any question? So similar to the single random variable case, the joint probability mass function is also called joint probability density function. So you can view these two terms like PMF and PDF are exchangeable even for discrete random variables. For discrete random variable, okay, when they talk about the joint density function, they're actually talking about the joint probability mass function. Okay. Okay, so here's our definition, right? So what's the property of a joint probability density function for discrete random variables? They must satisfy the following properties. So first, the value of the joint PDF must be always non-negative, meaning that whatever input value A and B you can take, as long as it's in the range of the random variables x and y. So your when you evaluate your PDF at A and B, the value must always be non-negative. Why is that case? Why is this true? Yes, exactly, right? This comes from the definition, right? So remember the joint PDF is actually just a special probability, right? The probability of special event, that is the event x equals to A intersection with the event x equals to B, right? So if you look at the probability for any event, right, it cannot be negative, right? It could be zero, but it cannot be negative. That's why the probability density function must always be a non-negative. The second thing is that if you sum over all possible configurations of A and B, and calculate the summation of the PDF function, it will be 1. Why is that true? Why is that the case? Why you sum over all possible values of why you sum the value of f, right, over all possible configurations of AI BIs will be 1. Any thought? Yes, exactly. So again, this is reduced to the definition of the PDF, right? So definition PDF for discrete random variables is just the probability for some special events, right? And when you enumerate all possible values in A and BG, you enumerate every possible event in the event space, right? Now you add to the, and all those events are not overlapping with each other, right? So like this guy could be, let me write it in a better way. This guy could be like x equals to 1 and y equals to 2. And this guy could be x equals to 1, y equals to 1, right? This guy could be x equals to 2, y equal to 1. This guy could be x equal to 2, y equals to 2. You see, every such event is not overlapping with each other, right? And we'll add all events together, all the probability of all events together, the summation must be 1. Any question? Okay, yeah, that's our basic definition of the joint probability density function. So let's rest for 5 minutes and then continue. Okay. Let's continue. So we have just introduced the definition of the joint probability density function for discrete random variables. Let us look at some concrete case, right? So just to follow the definition, and we have a better understanding, right? So here we're gonna introduce two binary random variables. So this on the context is called binary communication. So you can imagine that, like, okay, suppose I have there is a sender, there's a receiver, right? So the sender sends some message into some receiver, either from wireless network or from from physical lines and so on, right? So those network always have some issues and some errors. And here we talk about a wireless network, right? So that means like every bit sent by a sender has some probability of being corrupted. Okay? So there's no guarantee that, okay, you're gonna have 100% accurately or transmit your information. There is always some like errors or corruptions. So here we introduce two random variables. S represents the sent bit. Right? S is either 1 or 0. We just talk about 1 bit, or sending and receiving 1 bit. And R is the received bit. Right? So there is some chance that S and R are different. So we want to look at what's the probability, what's the joint probability your S and R take different values. So that gives us a joint probability density function or joint probability mass function, right? Because this is a discrete random variables, each random variable can only take 2 values. So of course, this PMF or PDF can be represented by a table. Right? So this is an example of this table. So what does this table tell us? So from this table, we can see that the joint probability of S equals 0 and R equals to 0 is 0.45. Is here. Okay. The joint probability of S equals to 1, R equals to 1 is 0.41 is here. Okay. So this actually represents the cases that the receiver receives exactly the same bit sent from the sender. Okay. But there are other cases. There are chances that your sending bit is 0, but receiver receives 1, right? That means the bit is flipped. This probability is 0.08 is here, right? And the joint probability S equals to 1, meaning sender send a bit 1, right? 1 bit, send 1, but receiver receives 0. This probability is 0.06, right? So you see there's some like a small chance that you receive the flipped bit, right? That means your bit is wrong. Like, any question regarding this example? Right? So this table actually defines the PMF function. It's split over what? Okay, so that's something we need to check, right? So want to check if we combine all the cases, the total probability would that be one, right? Yeah. So we have 4 cases, right? S equals to 0, R equals to 0, S equals to 1, R equals to 1, S equals to 0, R is 1, S is 1, R equals to 0, right? The 4 cases. And if we add them together, this will give you 0. You just add the 4 numbers together, right? Which gives you 0.86 plus 0.08 plus 0.006, which is 1, right? So this actually is a valid PMF function. And also, you have every entry of this table is non-negative. So this is a valid PMF. Any question? Okay. So a second example, like if you roll 2 dice, right? If you roll die for twice, or if you roll 2 dice, that's fine, right? That's both are fine. So we want to look at the outcomes of these 2 dice rolls and X and Y. So actually you're gonna see 2 points, X and Y, right? So, and here we define the joint PMF or PDF is for any pair of the points is 1/36. So the basically saying, you see any point for the first die is 1/6, and you see any point for the second die, you see 1/6. So their joint probability is 1/6 times 1/6, which is 1/36, right? So this PMF function also forms a table, right? It forms a 6 by 6 table. Why? Why is it a 6 by 6 table? Yes, exactly right. For every X, for X and Y, they both, they both has 6 values, right? So if you look at this PMF, the combination will be 36 entries. That's why when you draw a table, imagine right? So you're gonna have 6 rows, which represents all the possible values X can take, and 6 columns. Represent all the values Y can take, right? And every entry is the PMF value for the corresponding XY, right? Which is 1/36. Everyone's comfortable? I think, yeah, we hope this is like a relatively straightforward. Okay, so if you are given a joint probability function, joint probability mass function, or PDF or table, right? So we can calculate the so-called marginal probabilities. So that's mean, right? So right now we have this 2-dimensional function, right? Represents the joint probability density function for X and Y, right? So naturally we want to compute what is the marginal probability density function, or PMF, right? For X and for Y. Right? How can we do that? It's very simple. You just sum over the other side across all possible values it can take. Then you get the marginal probability. For example, if I want to look at what's the marginal probability density function for x at A, what do you need to do? You just fix A and sum the joint PDF with different choice of y values. So that means all those BIs. Then you get your marginalized PDF, which is for the variable x. Right. Similarly, if you want to get the marginal or probability density function for y, you're going to marginalize out x. Right. If you want to evaluate what's the PDF of y at a value b, right? So you're going to fix b and sum over all possible values of x, namely those AIs, right? And you add them all together, you will have the marginal probability that y equals to b, which is the PDF for y. Any question? Yeah, this is just the definition. It's quite straightforward. Right? It's like I'm gonna marginalizing means that okay, I'm gonna aggregate all the effect of other factors, right? So your PDF, the joint PDF or joint PMF actually specifies the probability of the two variables when they take different values, right? So now if you want to know the PDF for a single variable, you have to aggregate the effect of all the values of the other variables, right? This aggregation is done by simply summation of the joint PDF over the other variables values. Any question? Okay. So now comes to our example, right? So this is our binary communication example, right? We have this a joint probability density function for S and R, right? This represents F, right? The PMF for PMF or PDF for S and R, right? So now, what if I want to compute the marginal probability density function for R? Namely, I want to compute F R. How can I do that? How do we compute the PDF for the random variable R? Yes, exactly, right? So, I mean, we're going to start with the definition. If we want to look at what's the PDF for R, right? Take any value of R, right? You're going to marginalize out S, right? By marginalization, we mean you're going to sum over the joint PDF. You fix R, right? You sum across all possible values of S, right? So of course, to get the full version of FR, you need to consider two possible values, R equals to 0 and R equals to 1, right? For R equals to 0, right? You're gonna fix r equals to 0. You just sum over all possible value of s, right? That basically means, okay, I'm gonna fix r equals to 0, and just sum over all the rows in that column, right? Right, which is what is that? What's this summation? What? Yeah, 0.5y. It is just the 0.45 plus 0.06, right? Which is just the first row, right? Or first column, right? Which is 0.51, right? And similarly, how do we compute FR1? Yeah, just add up all the other column, right? So mathematically, we're just marginalizing S again, right? Well, we fix R to be 1. That means we're gonna add up the second column, right? Which is 0.08 plus 0.41, which is 0.49, right? Any question? Okay, yeah, then let us try to marginalize out R, right? If we want to compute the PDF for S, and then we need to marginalize out R, right? Again, you have two possible values for S, 0 and 1, and that means when we compute S equals to 0, right, we're gonna marginalize out R while fixing S to be a 0, right? And how do compute this? Which numbers should we add? Any thought? Yes, right? So if you fix 0, S equals to 0, right? You sum over all possible R values. That basically means that you're gonna sum the first row, right? Which gives you 0.45 plus 0.08, which is 0.53, right? And consider the case where S equals to 1. If you want to calculate the PDF for S and look at when S equals to 1, what is the PDF value? Again, we're going to marginalize out R. We'll fix S equals to 1, right? So how to get this summation? Yes, that's the second row, right? That's just the second row, which is 0.06 plus 0.41 equals to 0.47. Does it make sense? Right. So this is if you got two random variables, and if you want to calculate or if you want to marginalize out some variable, that corresponds to either adding all the numbers along one row or one column. Okay, but we need to understand why it is just to adding one column and one row. Right? This is essentially the summing over the random variables for fixing the other. Okay, so let us look at another example. you flip two fair coins. Two fair coins means that you have the equal chance to see a head or a tail, right? So we introduce two random variables, H and B. H is the total number of heads. So remember, we view heads as one, and we will tail as 0, right? So H is the total number of heads, and B is a binary number the two coins represent. So what does it mean? Like, for example, if your first outcome is 1 and second outcome is 2, then what is B? B is just 2, right? It's a binary representation, right? If you put these two binary outcome together and convert it into a number, which is just the 2, right? And on the other hand, like if you both, this is B, right? It's just 2. If both outcomes are ones, then if you use them to construct a number, what is that? It's 3, right? 1, 1. It's a binary number. It's 3. Any question? I mean, is there any question regarding the definition here? Right. So B is representing, like if you have a 2 digits, right? 1 and 0. If you put them together, what kind of binary number it can represent, right? So 1, 0 just represent binary number 2, right? If you represent number 2 as a binary number, is 1, 0, right? Okay. If you represent 1, 1, this binary number 1, 1 actually represents 3, right? In the decimal format, right? And if it is 0, 1, what is B? It's just 1, right? And if it is 0, 0, what is B? With 0, 0, what is B? It's just 0, right? Yeah. Because if you put this two 0 together, it's just represent binary numbers 0, right? This is a B, right? And for A, remember A represents, sorry, not A, H. H represents the total number of heads. So that means like when you have the first outcome is 1, the second outcome 0, what is value of H? 1, right? And when you have both outcomes 1, the value of H is 2, right? And 0, 1, the value of H is 1, right? And 0, 0, the value of H, right? So now it will be very interesting to say what is the joint probability density function for H and B. Right? Let's try to make this table, right? I'll put it here. This is H, this is B. Oops. Sorry. B has 4 possible values. H has 3 possible values, right? So zero, 1, 2. That's for H, and 0, 1, 2, 3. That's for B. Okay, let us try to fill this table, right? Filling this table means that we're calculating their joint probability density function. What's the What's the value here? Right? So this entry, right, represents the probability that H equals to 0 and B equals to 0. What's that probability? Yeah. You see that it only corresponds to one outcome, right? 0, 0. And what's the probability you say both outcomes are zeros? What's that? You threw a fair coin, right? And each flipping is independent to each other. What's the probability? Yeah, 25%, right? You got 1/2 chance, right? To say the first outcome is 0, and another 1/2 chance to say the second outcome 0, which is total. It gives you 1/4, right? 25%. Okay. So this guy will be 1/4, right? And similarly, we can compute the value of other entries, right? Some entries, the value probably is just 0 because it's impossible even. Okay, we're gonna fill the detail of table on Thursday. Okay? See you on Thursday.